So we've talked about vector spaces in R2 and R3. We've also talked about subspaces of the collection of m by n matrices or n by n matrices. It's also possible to have vector spaces of functions. So, for example, if we pick a particular interval to be our domain, and we look at the collection, so I've just made this notation, script f of I, so this is going to be all functions on I. And so here's the interval I, and we could have a continuous function like this green one, we could have, or this orange one, or we could have a discontinuous function, whatever, just the collection of all functions on this interval. That forms a vector space, because if I take two functions on I and I add them together, I get another function on I. And it's got the zero function, the function which is whose graph coincides with the picture of the interval I, just the zero function. And if I take any scalar multiple of a function, I get a function. There's a lot of interesting subspaces of this vector space. So for example, if I take C of I to be all of the functions from taking inputs from I and outputs in the real numbers such that f is continuous, well, a sum of continuous functions is continuous, and a scalar multiple of a continuous function is continuous, right? If I take something like sine of x and I scalar multiply it by 2 sine x is still going to be a continuous function. So the continuous functions form a subspace. And if I look at, say, C1 of I, so this is all the functions from I to R, such that the first derivative of f is continuous. And I guess I'm not saying it, but I should say is continuous on I. I guess it's sort of, well, implied. But then this is also a subspace. And why is that? Well, you know that if you take two differentiable functions and you look at their sum, then the first thing you learned about derivatives is that the derivative of a sum is equal to the sum of the derivatives. And so since f and g were both picked to be from this vector space C1, we know that this guy is continuous and this guy is continuous. Therefore, this whole thing, the derivative of the sum, must be continuous. So it's closed under scalar multiplication. And similarly, we know that the derivative of a scalar multiple, well, derivatives ignore constants, so we can just pull the constant out front. And we have a scalar multiple of something that's continuous, so it's definitely continuous again. So the differentiable functions form a vector space as well. And let's see what else. I could say let's let V be the collection of functions on some interval such that f double prime minus 3x f prime plus e to the x f equals 0. Well, let's see. Is this a vector space? So what am I asking? I'm asking if the set of solutions of some second order linear ODE, is that a vector space? Well, let's see. So suppose I let f and g be elements of V. Okay, so maybe this would actually look better if I replace this f here with y. Okay, that makes me a little happier. Okay, So let's suppose that we have two solutions to this differential equation. Okay, then following our method, what do we do? Well, then we know that f double prime minus 3xy, f prime plus e to the x f equals 0. And we also know that g double prime minus 3x g prime plus e to the x g equals 0. Okay, so what about f plus g? Well, let's see. So then if I'm going to figure out whether or not this is in there, then I'm going to have to substitute f plus g into this equation. So remember, I'm in V if I satisfy this. So I'm going to have to substitute f plus g into that equation and see what happens. So when I do that, I get f plus g double prime minus 3x f plus g prime plus e to the x f plus g equals 0. Or sorry, no, we don't know that it equals 0. That's what we want to check. Okay, so what can we say about this? Well, just evaluating the derivatives, I have f plus plus and g plus plus, and then here I'm going to have minus 3xf prime plus 3xg prime plus exf plus e to the x g. And so now I will take the f terms and group those together. And I will take the g terms and group these together. And then since I picked f to be a solution to this differential equation, I know that all this is equal to 0. And since I picked g to be a solution to the differential equation, I know that all this is going to be equal to 0. So I get 0. And so f plus g is an element of V. And if I look at a scalar multiple, then I'm going to have to substitute this scalar multiple in. So I'm going to have this scalar multiple double prime minus 3x cf prime plus e to the x cf. And what can I do here? Well, let's see. So this is going to be cf double prime minus 3xcf prime plus e to the x cf. And I can factor out a common multiple of c all the way through. So I have f double prime minus 3xf prime plus e to the x f. And so this part here, since we took f to be a solution of the differential equation, is 0. So I end up with 0. And that tells me that a scalar multiple of a solution is again going to be a solution to the differential equation. And this is actually secretly the reason why linear differential equations are defined the way they are. So if u and v are solutions of a linear ODE, any linear ODE, then so is AU plus BV. So this is sometimes referred to as the principle of superposition. And we've seen this in the homework exercises. That's the physicsy name for it because the physics people like everything to sound fancy. The math name for it would be saying that solutions of a linear ODE form a vector space. And let me be precise. A linear homogeneous has to be set equal to 0 or it doesn't work. Linear homogeneous ODE form a vector space.